Welcome to JC Connect. Yesterday we were discussing about the different properties of this quartz aggregate. In that we have discussed the specific gravity and the strength aspects. So now we'll start with the bulk density and the voids. Of course, the bulk density and the specific gravity are interrelated. Of course, if any variation in the specific gravity, there is of course there is a variation in the bulk density also. So of course bulk density is always related to the moisture content that are present in the aggregates. If moisture content is more in the aggregates, normally your bulk density is more. So then of course it depends on the particle size, grading and the moisture content, and mainly it is based on the moisture content. A higher the bulk density of the quartz aggregate is an indication of fewer voids to be filled by the sand and cement. Means if high bulk density is there, means it's a less voids. Then if less voids are there, of course that less void should be filled the by the sand and cement. Okay, that proportion should not be like what if less voids are there, normally what will happen is that whatever the quantity of sand and cement if you are going to use, of course it is less. But normally if you are talking about 1 is to 2 is to 4, that ratio has to be maintained, and it should not be less. It should not be like what you're not supposed to use less cement and sand also. Means that proportion is there, that proportion of the cement and sand you have to use it along with the voids. So of course some of the sufficient void should be there, and it should not be more also, and it should not be less also. So it should be some constant range of void should be maintained, so that proper cement and sand should be placed in between the voids that are present in the concrete. If the voids are more in the concrete, the strength of course it will be low. So then the porosity, of course the voids and the porosity is almost similar value, but when you are calculating the porosity, we will calculate it as a voids fractions. So how much fractions of voids are there? um, uh, when it is more voids, of course it is a more porous in nature. But when you are talking about this porosity, there the voids will speak about the in between the two aggregates. If any voids are there, that will discuss it. But when you are talking about the porosity will discuss uh, if you consider one aggregate, if the aggregate is cracked, mm, um, in that we'll see about this porosity. Means porous aggregate means, is there any crack in, is there in between the aggregates, not between the two aggregates. It is the single aggregate if you consider it. In that you have any um, cracks are there, whether in that cracks any air is entrapped or not, that you have to check it. That will tell about this porosity. The the entrapped air bubbles in the rocks during their formation lead to minutes holes called as a pores or the cavities. This porosity of the rocks is less than 20%. As for the standards, it should be less than 20%. There is no such cracks should be observed in the uh, rocks. Otherwise what will happen is that the air will entrap into that cracks, or the water will entrap, and the bulk density is going to increase. If the bulk density is going to increase, of course the strength of the uh, overall concrete is going to reduced. The concrete becomes permeable and affects the bond. This is very important. The bonding between the uh, aggregate, the cement and the sand is very important. If any cracks are observed in the um, uh, in your aggregates, normally it is going to affect the performance of the concrete. The porous aggregate absorbs more moisture and resulting the loss of the workability. If loss of the workability is happening, of course it is indirectly affecting on the strength of the concrete. So then, moisture content. A high moisture content increases the um, water to cement ratio, of course, to an appreciable extent. And normally, if moisture content is increasing, it will increases the water to cement ratio or water to binder ratio, that is 0.45 is the standard. So when it is increasing, normally what will happen is that uh, normally it reaches 2.5, or sometimes it will increase up to 0.6. So if it increases above 0.45, normally the workability is going to decrease. Of course, the strength is also going to decrease. So the surface moisture expressed as the percentage of weight of the saturated surface by the dry aggregate is known as the moisture content. So this is how we can define it. You take the aggregate, you weight, then what you can do is that, then after drying, take the weight, then what you can do is that the same amount of aggregate you put it in the water and take it out and measure the weight of that, and you take the percentage weight of the dry as well as uh, the wetted aggregates, multiply by 100. So that will give you the how much um, how much water content is absorbed, that is in bulk condition. And suppose one more test you can do is that, take the normal aggregate. Initially you take the weight of that when you take it from the field, then dry it, again you take the weight, then after own drying, weight, and before own drying, weight, and you take the ratio of after own drying divided by before own drying, multiply by 100. So that will give you the how much moisture content that is exist in the aggregates, that is under normal conditions. So the previously what we have discussed, that is under bulk conditions, means by inserting into the water media and find outing how much it is absorbing. So um, deleterious materials and organic impurities. So deleterious materials, it will includes the content of salt and the sulfate content. Normally it is observed in the aggregates. And the organic materials like um, clay, shale, and some of the coal and iron pyrites, which contains carbon as the main content in their structure. Some of the aggregates has the compositions of this, so which is going to affect the chemical composition of the chemical reactions between the aggregate, the cement, and the sand, which affects the properties of concretes. And of course these are all undesirable. Of course, this detritus materials, I already said that the salts and the sulfides or the sulfates which are present in the aggregates, and that I already explained with respect to the chloride attack and the sulfate attack in the um, on the concrete. And of course this chloride and sulfate attack is nowadays is common, and that has to be studied properly. Alkali aggregate reaction, it is a very important reactions. Normally it is going to happen in um, the concrete. This whatever sometimes in the earth crust, naturally available alkali containing aggregates are available, means aggregate consists of around 5 to 6% of alkali percentage. um, that is very important when you are dealing with the reactions with the cement and the sand. Sometimes what we'll do is that to increase our strength, we'll add the alkalis, the sodium hydroxide type of course sodium hydroxide is one alkali that will add in our um, normal concrete to increase the strength. In that case what will happen is that there are some chances that um, this alkali is going to react with the aggregates. Then there will be expansion of the whole concrete. When the expansion of the whole concrete is going to increase, there is a voids is going to increase in between uh, the the sand and the aggregate. Then automatically the the strength is going to decrease. So of course uh, it is a common reactions. It has been studied in 1940. So extensive expansion and the complete disruption and the disintegration of the concrete is known as alkali aggregate reaction or the concrete cancer. Of course it is known as a concrete cancer. The trouble is due to the reaction between the silica in the aggregate and the alkalis in the cement. We already said that silica is present in not only the aggregate, it is present in cement and it is present in sand also. Silica is the main component. We cannot say it is only the alkali reaction is between the aggregate. The silica is present in the aggregate, the silica is present in the cement, the silica is present in the sand also. So when this alkali is going to react with this silica, that is sodium hydroxide, is when it is going to react with this silica content that are present in the aggregate as well as the cement and the sand. Normally there is silica gel is going to form. Then the silica gel is nothing but the expansion of the overall concrete, and automatically the strength is going to decrease. Reactive aggregate, if it is finely ground state, will inhibit the action. Of course whatever the action has to happen, that is going to decrease. A reactive aggregate, a reaction between the cement aggregate can be two types. One is either alkali with the silica or the carbonates with the aggregates. The first reaction is alkali with the silica. The second one is alkali with the carbonates. Normally some carbonates it will be there in the water as well as in the cement also. Some of the carbonates it will be there. Sometimes this alkali is going to react with the carbonates or the alkali is going to react with the silica, but more commonly the alkali is, but the less percentage of carbonates it will be available. So that is why the reaction between uh, the uh, the alkali versus carbonates is negligible, and that is why it is neglected. So the reaction between um, the silicon and this alkalis are the predominant, and it's more commonly observed. So this AR, that is alkali aggregate reaction, plays only in the presence of water and water vapors. Of course um, without the moisture content the reaction will not happen. The water forms a strong caustic solute with the alkali of the cement. Of course it will form the caustic solute, that is nothing but the gel. This caustic liquid attacks the reactive silica to form a silica gel of unlimited swelling type. Normally it is the swelling is continuous process, and it will continuous process, it is not going to end. So you can see this is how it is going to happen. We want to see this alkali hydroxide is there, that is nothing but your sodium hydroxide. Then silica is there, it is going to mix plus water. I already said that the reaction is going to, it's not going to happen without the water. So alkali, that is sodium hydroxide, plus silica is there plus water. So then it will give AR gel, means alkali aggregate reaction gel. This AR gel is highly hydrated in the presence of water, and reacted aggregate develops expansion. You can see that there is an expansion of the total cement. When the expansion of the total cement is going to happen, there is a formation of the cracks. Most of the time what will happen is that mm, even in the walls, concrete walls, if any cracks is coming, it is nothing but it is due to the expansion or the contraction. Normally the expansion is going to happen. Even in the contraction, if the percentage of silica, if it is going to decrease, normally the uh, whatever the reduction in the or um, cracks is going to happen due to the percentage of decrease in the silica. And make sure that when expansion means, uh, when this alkali aggregate reaction is going to happen, normally the expansion is going to happen. When the contraction is going to happen, you can see the cracks that are found in the concretes. You can see here in this, sometimes there will be expansion of this aggregate. When the expansion of the aggregate is going to happen, you can see that there is even in the columns, even in the beams in this pictures. This is how the alkali aggregate reaction is going to happen. So factors affecting the alkali aggregate reaction. So reactive type of the aggregate has been found to be have a serious effect if present in a small quantities, but not if it is constituents of whole of the aggregate. If I already said that if the alkali, I already said that it is 5 to 6% it will be present in the aggregate. If it is there with 1 or 2%, if it is crossing 10 more than 3% or 6% or more than 10%, of course it is going to increase the alkali aggregate reaction, then it is going to decrease the strength of the concrete. High alkali content of the cement. If there is a very small amount of the alkalis in the cement or very reactive silica is not a problem. However, increasing the alkali content of 0.6% of the cement was the issue of the AAR. Of course, this alkali, I already said it is with respect to the silica. If silica is absent, assuming that if the silica is absent, only alkali is there, then there will not be any reaction between the um, alkali aggregate reaction. So then there will not be any problem of the increasing the um, uh, increasing or expansion of the uh, this cement. So then will not be any problem. Even its meaning is that only high content of alkali with a less content of silica, it is not going to obstruct or increasing the uh, expansion of the concrete or the formation of the gel. Then it is very importantly, when you are using high content of alkali, make sure that it consists of very less silica. So availability of the moisture content is also very important. If no moisture content is there, the AAR will not happen. So of course the temperature condition should be favorable, generally in the range of 10 to 38 degree. Normally this type of condition should be favorable, not less than 10 degrees centigrade. Normally if less than 10 degrees centigrade, the moisture content is going to increase. If the moisture content is going to increase, of course, so AAR, the reaction is going to increases, or it will be favorable. If the AAR reaction is favorable, normally your strength of the total concrete is going to reduced. Then how to control this AAR? Of course, by selecting non-reactive aggregate, means free from um, alkali containing aggregate, 0 percentage of alkali aggregate. By using low alkali cement, sometimes you can use the low alkali cement also. By controlling the moisture content, as I said. Then by using some of the pozzolas, like some of the fly ash, surki, lime, which is going to decrease this AR reaction. By adding some of the air entrampment agents, normally if the bulging is going to, or if the gel is forming, so normally that gel can be suppressed by using some of the nitrogen gas or entering the nitrogen gas into the um, concrete, which is going to decrease the AR reaction. Soundness test. The soundness is defined as the ability of the aggregate to resist the change in the volume as a result of the change in the physical condition. Of course, soundness will affect on the change in the volume of the total aggregate or the cement. The conditions like freezing, thawing, temperature change, alternate wetting and drying causes the soundness of the cement. The porous and weak aggregates undergo excessive volume change under these conditions. As we already discussed, more porous concrete will affect the soundness of the concrete. Or the weak aggregate. Weak aggregate means I already said that when it comes to the porosity, it is the cracks that are found in the aggregates. When the cracks are forming, um, then of course the soundness of the concrete is going to decrease. Soundness of the concrete, it is going to increase. Sorry, the soundness of the concrete has to be increased. So thermal properties. So the coefficient of thermal expansion of the concrete increases with that the coarse aggregate. Normally what will happen is that mm, there are many coefficient of thermal expansions are there for each of the building materials. What is this coefficient of thermal expansion? For example, if you go on increasing the temperature on the aggregate, how the expansion of the aggregate or the wall increase in the change in the volume of the aggregate is going to happen. For example, you take cement or the sand, go on heating cement or the sand, check that how the volume change in the volume is going to happen or the expansion is going to happen with the increase in the temperature of the unit increase in the temperature. Then if unit increase in the temperature is going to happen, how the thermal expansion is happening. So the coefficient of thermal expansion will tells about how much expansion is going to happen by increasing the temperature of the temperature on the each of the building materials. So each of the building materials is having separate coefficient of thermal expansion. So then any difference in the coefficient of the coarse aggregate or cement paste may break the bond between the, of course sometimes if you increase the temperature in the concrete, normally the bond between the aggregate and the cement is going to break when that is nothing but total thermal expansion of the concrete. Normally if it increases more than 500 or 600 or 700 degrees centigrade, normally the thermal expansion is going to happen. When the thermal expansion is going to happen, normally the breaking of the concrete is going to happen. When the breaking of this concrete is going to happen, means the bond is going to break in between the concrete, and of course the total overall efficiency of the concrete is going to decrease. Of course the thermal expansion of the aggregate, the thermal expansion of the cement and thermal expansion of the sand should be studied properly, then in separate overall efficiency of the concrete can be studied. Then this fineness modulus we will discuss in later, the next class we will discuss it. Thank you.